Hello, welcome back. In this section, we're going to be talking about geometric sequences and series. Now don't be concerned, there's no geometry involved in this. It's just a name. So when we talk about a geometric sequence, we're talking about a sequence where the ratio of any term to the previous term is constant. So when we say ratio, what we're talking about is a fraction or division. And we call that constant ratio the common ratio. So let's look at a couple of examples and try to determine whether these sequences are geometric or not. So for the sake of our example, I'm going to name each term in this sequence. So I'm going to have A2, I'm going to say A1 is 4, A2 is 10, A3 is 18, etc., etc., etc. So for this to be geometric, the ratio from one term to its previous term must always be constant. So the first ratio we can write is the ratio between 10 and 4. So we have A2 over A1. So that first ratio is 10/4 or 2.5. The next ratio we can write is between 18 and 10. So that's A3 over A2. That would be 18 over 10 or 1.8. And right here, we can stop because we notice that the ratio between the first two terms and then the second and third term are not the same ratio. So right away, we can tell this is not geometric. Okay. If we do the same thing over here, we'll say A1 is 625. A2 is 125, A3 is 25, A4 is 5, and A5 is 1. So just like before, we're going to start by taking the ratio of the first two terms. So A2 over A1, so that's 125 over 625, which is equal to 0.2. Then we'll do A3 over A2. So that's the next two. So that's 25 over 125, which is also 0.2. That doesn't mean we're done, though. That just means that so far we can conclude it's geometric. We have to check them all. So let's look at the next pair. So that's A4 over A3. Which is 5 over 25, which is also 0.2. And then my last one, A5 over A4, which is 1 over 5, which is also 0.2. So what we conclude here is that this is geometric, because my ratio for all of my known terms, or pairs of consecutive terms, I should say, is constant. I got 0.2 each time, and just 0.2 is 1/5. So the way you can think about this, the other way that doesn't involve using the definition explicitly, is if we look at here, to go from 625 to 125, we multiplied by 1/5. To go from 125 to 25, we multiplied by 1/5. To go from 25 to 5, we multiplied by 1/5. To go from 5 to 1, we multiplied by 1/5. What we've done here is the same thing as what we did here. It was just involving a lot less writing. Now, sometimes it'll be really easy to look at the sequence and tell if there's something that's being multiplied each time. I would be willing to bet that most of us would have looked at 625, 125, 25, 5, and 1 and not being able to see that we're multiplying by that fraction of 1/5 each time. So going and using the definition here was probably the best way to go. Although, if you would have looked at that and you were to notice that, hey, we're just multiplying by 1/5 each time, what I've done here in the yellow is equivalent to all of this stuff we did here in the green. So keep that in mind. Some of them it'll be very easy to tell if they are geometric or not, just by kind of looking for something that's being multiplied at each step. Okay, so the next thing we're going to want to do is be able to write a formula for our geometric sequence. So the formula for our sequence is a sub n, so that's the nth term, is equal to a sub 1, so that's the first term in our sequence, times r, which is that common ratio, to the n minus 1. And n is like the term number in our sequence. So let's look at a couple of examples of working with this. So if we want to write the rule for this sequence, and let's say we have the sequence 4, 20, 10, 500, etc. So the first thing we would want to do is determine what type of sequence this is. So in this course, we've seen two different types of sequences. We've seen arithmetic, and we've seen geometric. Now there's a lot more, but in this course, all we're going to worry about are those two. So we have to determine which one we're working with, arithmetic or geometric. So if I look here, if I'm thinking it's arithmetic, to go from 4 to 20 would be 16, we'd be adding 16. But to go from 20 to 100, we'd be adding 80, so it's clearly not arithmetic. To go from 4 to 20, we multiplied by 5. To go from 20 to 100, we multiplied by 5. And to go from 100 to 500, we multiplied by 5. Here we're definitely dealing with a geometric. Now this is a situation where hopefully looking at these numbers, it would be easy to kind of see that we're just multiplying by 5 at each step. If you didn't notice that right away, you could have certainly written the ratios out like we did in the previous examples. But here it's a case where hopefully this was easy enough multiplication that you could have seen that and just written what I've done there, which is an equivalent steps. It's doing the same thing. It's just a lot less writing and it's a little quicker, especially in the case where it's obvious. Okay, since it's geometric, we know the formula that we're going to use is this one. So we want to write the nth term. So there's the nth term. And we need the first term. Well, that's the first term, times r, which is the common ratio. That's my r to the n minus 1. And I'm done. It's that easy. Okay. What if we do, to follow up on this, what if I ask then what is, say, A7? Well, I have a rule that we just made from this geometric sequence. So all I'm going to do is plug 7s in for n. And then I'm going to just fire up my calculator and type this in. Four times 5 to the 6th. So I get 62,500. So those should be that's a pretty easy situation, right? It's pretty easy to find r, and you already have the first term, so there's not much to do. So let's look at another example that's a little more complicated because we give you a little bit of different information. Okay. Let's say we ask you to write the rule for the geometric sequence where the fourth term is 12 and the constant ratio is 2. Well, since we're told that it's a geometric sequence, the rule that I'm going to be using is this. Now we have the value for r already. What we're missing, though, is the value for a1. Instead, what we're given here is this is a value for n, and this is a value for a sub n. So what I can do is I can plug these in and then use that to solve for a sub 1. So 4 minus 1 is 3, and 2 to the third is 8. And if I divide both sides by 8, I get 12 over 8, which reduces down to 3 over 2. So we can say then, a sub 1, my rule is the first term, 3 over 2, times 2 to the n minus 1. Okay, so not too bad, right? We just had one extra little solving step, but it wasn't a super difficult solving step. Let's look at the most difficult of these situations. So let's say we want to write the rule for the geometric sequence where the third term is negative 48 and the sixth term is 3072. Okay, so we know we're dealing with a geometric sequence. So the form of our rule is going to look like this. Now, to solve this, we don't have our first term, and we don't have the common ratio. So we have two variables to solve for. To do that, we're going to have a system of two equations. So what we have here is an n and an a sub n, and a different n and a different a sub n. So this is going to allow us to write one equation from this point, and then a separate equation from this. And that's going to form a system of two equations. Now we're going to solve this system by using elimination. However, you'll notice in this problem it's a little bit different than the kinds of problems we solve for in first semester, because the two variables we have in this situation, instead of being added together, are being multiplied together. So in an elimination situation where my variables are being multiplied, instead of like adding and subtracting the equations, I'm going to really just be multiplying or dividing these equations. And I notice right away if I take one of these equations and divide it by the other, that the A1s will cancel out. So that's what I'm going to do. And in general, what I'm going to do is I'm going to take the equation with the bigger exponent and divide it by the equation with the smaller exponent. So I'm going to do equation B divided by equation A. So the right-hand side of that is going to be 372 over negative 48. And the left-hand side of that is going to be A1 times r to the 5th over A1 times r to the 2nd. 6 minus 1 is 5. 3 minus 1 is 2. That's where the exponents came from. So I notice here that the A1s are going to cancel out. Then if I look at my r's, this is a rule for exponents, right? We said a to the n over a to the m is equal to a to the n minus m. So here I have 372 over negative 48 is equal to r to the 3rd. And to solve for r, what I'm going to do is I need to cancel this exponent of 3. So to cancel this exponent of 3, we'll just take the cube root. And remember, since this is an odd root, I don't generate a plus or minus. It's fine the way it is. So I'm just going to go into my calculator and evaluate this. Cube root of 3072 over negative 48. So to get the cube root symbol, I'm going to press the math button and scroll down and find the cube root symbol. And then I'm going to type this fraction in. So I'm going to use the fraction command. To get to that, I press alpha, the y equals, and I usually just use the improper fraction one. So I can type this in exactly as it looks on my sheet of paper. When I do that, I get negative 4. Okay. So now I know r. If I go back, we got this one. We still, however, need the first term. But what you'll notice is this is now turned into the previous problem. Because I know a term. It doesn't matter which one you pick. For the sake of argument, I'm going to pick the smaller one. And I know r, and I just have to find A1. So if I do that, I can say negative 48 is equal to A1 times negative 4 to the 3 minus 1. So if 3 minus 1 is 2, negative 4 squared is 16. And to get the A1 by itself, we'll just divide both sides by 16. So I get that A1 is negative 3. Now that I have A1 and r, I have everything I need to write my rule. And I'm done. Next up, we're going to talk about geometric series. So for a geometric series, there's two situations that we have to consider. We have finite geometric series, and we have infinite geometric series. Unlike the arithmetic series, where all the infinite series were either positive infinity or negative infinity, they were essentially divergent. Some of the infinite geometric series are calculable. So what makes them calculable? It has to do with the magnitude of that common ratio. the magnitude of that common ratio is less than 1, then those infinite geometric series do have a sum, and we can calculate it. So let's look at some examples. So let's say we're asked to calculate the sum of this series. So we have the sum from 1 to 16 of the sequence 4 times 3 to the I minus 1. Now when doing these, we have to be really careful about looking at the form of our sequence. First thing I need to do is identify whether this sequence here, that its formula is a geometric or arithmetic sequence that we're summing. That makes a big difference because we have a separate formula for each of these situations. So I know that this is geometric because the form of the geometric is this. And you'll notice that I have my index variable in the exponent. So that's really what kind of indicates to me that this is a geometric. So the formula I'm going to be using is this one from up here, because that's the formula for a geometric. So I know that this is equal to the first term. Well, how do I get the first term? I'm just going to plug 1 in for I. And I have 1 minus R. Well, I know that the form of this tells me that this guy is R. To the N, I know that this guy up here is my N over 1 minus R. And now I'll just go to my calculator and type this in. So I have 4 times, and then I'll do my fraction command just like we did earlier. 1 minus 3 to the 16 over 1 minus 3. So I get 86,093,440. Let's do another. So again, first thing I'm going to do is I'm going to look at the sequence that I'm summing over. And again, because I notice the index variable is in the exponent, I know that this is geometric. And I can tell right away, because the form of a geometric is this, that -2 is my R. Okay. Next thing I'm going to do is I notice that this is an infinite geometric. So if I look at the magnitude of R, that's equal to 2, which is not less than 1, so that we can say immediately this is divergent. Let's do another. Again, first thing I'm going to do is look at the sequence involved. Again, this is geometric for the same reasons that we've seen before. It's infinite geometric, so immediately I have to check for my R. And here, the absolute value of R is 1/2, which is indeed less than 1. So we can calculate this. So S sub n is going to be the first term. So that's this over 1 minus R, which gives me 20. You could type that in your calculator if you couldn't do that in your head, which is fine. Okay. What if we give you this sequence, or this sum? So again, here the first step is going to be determining whether these terms that we're adding up come from an arithmetic sequence or a geometric sequence. So a quick check here tells me right away that it's not arithmetic. To go from 256 to 128, I subtracted 128. But to go from 128 to 64, I would have subtracted 64. So we're not arithmetic. But to go from 256 to 128, I multiplied by 1/2. From 128 to 64, I multiplied by 1/2. And from 64 to 32, we multiplied by 1/2. So this is geo, and the R is 1/2. Notice that it has a dot, dot, dot at the end. So this is the infinite situation. So because the R value is less than 1, I should say the absolute value of R is less than 1, and it's infinite, I know that this sum is going to equal the first term over 1 minus R, or 512. Okay, let's do one more. Okay, so let's say we have this one. So first thing I'm going to do is check to see if these terms come from an arithmetic or a geometric sequence. So to go, let's check arithmetic first. To go from 3 to -6, I'd have to subtract 9. But to go from -6 to +12, we would have to add 18. So already we know it's not arithmetic. Let's check to see if it's geometric. To go from 3 to -6, we'd have to multiply by -2. To go from -6 to +12, we'd have to multiply by -2. And from 12 to -24, we'd have to multiply by -2. So I know that it's geometric, and my R value is -2. So, since this has a last term, I know it's finite. So the formula I'm going to be using is this one. The one thing I don't know, I know A1, I know R, what I don't know is N. So I don't know the N, I don't know the term number for 3072. Well, we're going to have to find that in order to fill it into this formula. To do that, what I'm going to do is I'm going to write the geometric sequence here. So I know the geometric sequence is a sub n equals the first term times the constant ratio to the r minus 1, or to the n minus 1, excuse me. So I have 3 times negative 2 to the n minus 1. And now if I want to solve for the n, for a specific an, I can plug that in. And solve for n. And this kind of an equation should look familiar. In fact, we just got done solving something like this in the previous section. This is an exponential equation. So the first thing that I want to do is I want to divide by 3. So when I do that, I get 1024. It's negative 2 to the n minus 1. Now I have to be a little bit careful here, because when we solved exponential equations, we did not allow this base of our exponential to be a negative number here. Now, I'm going to know that this value for n is going to be equivalent to the answer as if this was a positive 2. How do I know that? Well, let's just pretend it works, and then we'll go back and check and make sure it's still, that this solution, when the 2 is positive, still satisfies this equation when the 2 is negative. So I would take the log base 2 of both sides, because I need to cancel that exponent base of 2. And we know the log base 2 cancels the exponent base of 2. And log base 2 of 1024, I can do that on my calculator. So just to remind you, if I press math, I go down and choose the log base command. My base is 2, 1024 is 10. And then when I add 1 to both sides, I get 11. Let's just double check up here to make sure when I plug 11 in for n, I get 1024. So if I do negative 2 to the 11 minus 1, I get 1024. So solving the equation where the 2 is positive gives me the same solution as if the 2 was negative. Now I have to do this because if you try to type log base negative 2 of 1024 in your calculator, it's going to give you an error. You can't handle it. But just use a positive base and you're going to get this an answer that works if the base was negative. Okay, so now we have everything we need, right? We have our n, we have our r, and we have our a sub 1. So all I need to do now is fill them in. So I have 3 times 1 minus negative 2 to the 11th over 1 minus negative 2. So I'm going to just type this into my calculator. So I have 3 times parenthesis alpha y equals 1 minus, and then I have to be careful with these negative 2's. I need to make sure that negative 2 is in parenthesis, and the exponent is outside of that parenthesis. The same thing here. So there's my, exactly what I have written down here. Press enter, and I get 2049. Okay, so that'll wrap up this section. You should now be able to do assignment 3, and good luck to you.